All right, everybody, hello and welcome back. Today, we're going to continue looking at sequences and series. So, for our very first sequence, we have 2, -6, 18, and -54. And then the sequence, is going to continue. Now, typically what we would do is we'd look and we'd say, okay, to go from the first term to the second term, we are subtracting 8. That's what we've done in the past, and that is what we would call an arithmetic sequence. However, if we look at the next pattern, to go from the second to the third, we'd be adding 24, which is not the same, right? Our sequences should follow the same pattern for the most part when we are talking about our specific sequences of arithmetic and then the one we're going to introduce today. So the pattern here is actually not going to be addition or subtraction. Instead, the pattern is multiplication. To go from 2 to -6, we are multiplying by -3. And then if we go from -6 to 18, again, we are multiplying by -3. So the pattern here is multiplication. Now, the big giveaway for us is we are going from a positive to a negative to a positive to a negative, and that pattern is going to continue. So it tells us what we're multiplying by. Our ratio is going to be a negative number. This is what we call a geometric sequence. And now a geometric sequence is a sequence where from each term, to go from one term to the next, we take the product of the previous term and a constant. What that means is to go from one term to the next, we are going to multiply the previous term and our common ratio. So that has a formula that we are going to use, and is going to have an explicit formula of a sub n equals a sub 1 times our ratio to the n minus 1 power. So if we look at our previous example from above, our explicit formula would be a sub n equals our first term times our ratio to the n minus 1 power. Now, the benefit of our explicit formula, once again, is if we want to find any term, let's say we wanted to find the 8th term, all we'd have to do is take our explicit formula and then plug in 8 for n. All right, and just to save time, we're not going to do the simplifying there, but what we end up getting is 2 times -3 to the 7th power. Let's take a look at a separate sequence here. We have 16, 4, 1, and 1/4. So we can tell that our sequence is decreasing. All right, by first glance, we might look at the first one and say, hey, we are subtracting 12 every time, but that pattern doesn't hold true from our second to our third term, so that should be our indicator that we are going to be multiplying. Here, the pattern is multiplying by 1/4. As you can see, that pattern is going to continue from our second to our third, and then our third, and so on. Now, a lot of people might look at this and say we are dividing from going from one term to the next. Geometric sequences are always multiplying by a ratio. So in this case, we're just multiplying by a fraction, which is why it is getting smaller. So if we want to come up with our explicit formula, we have a sub n equals our first term, which is 16, times our ratio, which is 1/4, to the n minus 1 power. Again, this is helpful because if I wanted to find the 100th term, instead of continuing my sequence on and on and on until we get to the 100th term, I can simply plug in 100 for n, and I would be able to find that value quite easily. So it is pretty similar to an arithmetic sequence. Our formulas are very similar. The difference is, instead of adding a common difference, we are multiplying by a common ratio. So let's take a look at a separate problem, and this is going to involve geometric series. So it says calculate the sum of the first 5 terms. Well, we've got 4 terms here, so we could just find our 5th and add them together, but that's not a very plausible solution when we have a lot of terms. Let's say it was the sum of the first 50. I wouldn't want to have to list out the next 46 terms in order to then add them together. So instead, we're going to use a new formula. The first thing we need to do is we need to find our pattern. So if we notice, to go from 3 to 6, 6 to 12, 12 to 24, hopefully we recognize we are multiplying by 2. Since we are multiplying, that means we are going to have a geometric sequence, which has an explicit formula of a sub n equals our first term times a ratio to the n minus 1 power. What we can do is use this by plugging in 1 to find our first term, we can then plug in 2 to find our second, and so on and so forth until we have the terms we need and then add them together. But again, this isn't very efficient. So instead, we have a couple different ways we can calculate the sum. What we've done in previous videos is we use our summation notation, which looks just like this. We have our Greek letter sigma, we have n equals 1 on the bottom, and what that means is we're going to plug in 1 first, so we'll find our first term, and then 2, then 3, then 4, all the way to the number that's going to be on top, which in this case is 5. What comes next is our explicit formula, which we have already found to be 3 times 2 to the n minus 1. And now we could do this directly on our calculator. If I pull up Desmos, I can just simply type in SUM, and we get our sigma value here, and then we can plug in the values we need. Now, when we type in our explicit formula, I always like to put it in parentheses just to avoid any potential issues. And then our exponent is also going to be in parentheses because we want our n minus 1 to all stay up in that exponent. So as you can see, the sum of the first 5 terms is 93. And we didn't really have to add any of our terms out. We didn't have to list them out. So this is probably the most efficient way we can do this. Now, there is another way. We do have what we call our finite sum formula, and the sum formula is going to give us exactly the same thing that we just got using our summation notation. So in this case, to properly use this formula, we are finding the sum of the first 5 terms. So that's why we have S sub 5. The S is for sum, 5 is for the first 5 terms. Then we have a sub 1, which is our first term, times 1 minus our ratio, which is 2, to the n power. Well, we replace the s sub n with a 5, so that means the n in our equation should also be a 5. And then we have 1 minus our ratio again, which is 2. Now, I prefer to always plug in values in parentheses. And the reason I do that is when we have negatives, if you were to skip out on our parentheses here and type this into your calculator, this value right here would simplify to something different than we want in certain situations. So just to simplify, I always try to plug values in with parentheses, even when they're not necessary in a case like this. So if we want to simplify, we have 3 times 1 minus, well, 2 to the 5th. We have 2, 4, 8, 16, 32. Divided by 1 minus 2, which is a negative 1. So we get 3 times a negative 31 over negative 1. And we end up with 3 and negative 31 gives us a negative 93 divided by negative 1 tells us our sum is 93, which is exactly what we got before. Now, in certain situations, the summation notation is going to be the easier way to find the sum or the value of a series. In other situations, our formula down here, the finite sum formula for a geometric series, is going to be more efficient. It kind of just depends on what information you are provided with. So we need to be comfortable using both of these. You should definitely practice with both and definitely make sure we work on plugging into this formula and simplifying on our own. If you are going to use a calculator, you are going to use Desmos, just make sure when you type it in, it looks exactly the way that this equation does. Okay? As always, thank you for listening. Just a quick recap. We've got a new type of sequence here, which is a geometric sequence. When to go from one term to the next, you're multiplying by a common ratio, and then you use this explicit formula. A sub n equals a sub 1 times a ratio to the n minus 1 power, which we applied to a new situation here. And we started to use it to find the sum of the terms in a sequence, to find the series, but we realized that that wasn't most efficient to list out all of our terms and add them together. So we think back to our previous activities where we have our summation notation, and for whatever reason, if we are unable to use a calculator, let's say, we could use our finite sum formula for a geometric series. And again, we have one of these for an arithmetic series, but those are going to be different because the sequence types are different, right? One is multiplying by a common ratio, one is adding by a common difference. And just as a quick recap, the arithmetic finite series formula is going to be this. All right, please excuse my handwriting. I am writing with my finger today because my Apple Pencil decided not to work. So I hope that clarifies everything for you. If you have any questions or concerns, as always, please feel free to reach out. Thank you.